The next team is Team 10, Energy Harvesting Sensor. Customer is Professor Ari Trachtenberg. Oh, go ahead. We have a...
So if it works.
So we are Team 10, and we're here to talk to you about our wirelessly communicating environmentally powered sensor, or WISEPs. I'm Pat, this is Eugene, Jing, Shayla, and Kevin. And our customer is Professor Ari Trachtenberg of the BU ECE department. So to start off, our customer has recognized these issues that the car industry is currently facing. Wire weight in the average car takes up about 3.5% of the weight of a car. So by reducing this weight, we could potentially increase a car's gas mileage by about 2 miles per gallon. An average 5-passenger car has a load capacity about 950 pounds, which is insufficient to hold 5 adult males, which are about 195 pounds each. So by reducing this weight, reducing the wire weight in a car, we can increase the load capacity and gas efficiency. Additionally, wires are really difficult to repair, and they also have expensive maintenance costs and pose possible electrical hazards. Additionally, pollution and global warming is a real issue, and automobile exhaust is a huge contributor to that problem. So in order to alleviate these problems, our customer has proposed an energy harvesting car sensor, and has also outlined this list of design requirements. Firstly, it has to be energy harvesting, which means it'll be powered by its environment. It has a low emission production. So in our case, we're using a thermal energy generator. So it uses a thermal gradient to produce electrical current. It also has to be portable and unobtrusive, with easy installation and maintenance, which means there's no wire connection to the vehicle. The device should also work autonomously and have a long life expectancy, so about like 5 or plus years. This means that the device has to have durable parts and a large number of recharge cycles. And lastly, the data that it collects has to be transmitted wirelessly to the customer's Android phone using Bluetooth. And Eugene will further describe the details of our system.
Okay, so our system begins in the car's engine, where the car's engine gives off thermal waste. That thermal energy is then harvested into our micropel TE core energy harvester. The TE core energy harvester stores any excess energy that it doesn't need inside of a supercapacitor, and the thermal energy operates under the thermoelectric effect, where small temperature gradients or large temperature gradients cause small currents, but powerful enough for us to power a system. So the power then goes to our temperature sensor, the TMP102, and the microprocessor that communicates over I2C with the temperature sensor, the MSP430 F5438. After the temperature is processed and transmitted to our microprocessor, it then gets transmitted again through Universal Asynchronous Receiver Transmitter, UART, to another microprocessor. The microprocessor receives the data is the MSP430 BT5190. The BT5190 is connected by another UART again to a Bluetooth module, in our case the CC2560. So then the Bluetooth module communicates by SPP to which is a serial port profile, which is similar to the RS-232 classical serial connection, to an Android running version 2.2 phone. Finally, the information is then displayed on our Android phone. Okay. So our Bluetooth microprocessor is a TI MSP 430 BT5190. Okay. So the MSP 430 BT5190 was chosen primarily for two main reasons. One, it's a leader in low energy usage, something that we require and absolutely need. It's able to operate at less than 1 milliamp at 8 megahertz. The other primary reason is that it also has a simple method to connect to a Bluetooth module, which is by UART, which then allows us to much more easily focus on actually developing our system and not figuring out the Bluetooth in-depth protocols involved. Okay. So for our Bluetooth was primarily chosen because for the Android phone there was primarily only two possible protocols we can use, either Wi-Fi or Bluetooth. Clearly, Bluetooth was chosen as the lower power communication system. Out of that, we chose the Panasonic 1315 Bluetooth module. The Panasonic 1315 Bluetooth module is able to communicate up to 10 yards, which is much longer than any car our system will be installed on. And it's also able to penetrate outside. Its signal strength is also able to penetrate outside of the engine's car compartment, which then allowed us to actually install it in an engine. So we use the serial port profile SPP, which is common to all updated versions of Android, which is once again similar to a serial port connection. And with that, we're able to communicate between our Bluetooth module and the phone. And now Kevin will discuss the I2C and sensors.
Okay. So due to low power constraints that we're subjected to, as Eugene mentioned earlier, we need a microprocessor and a sensor that requires as minimum power as possible. So for our microprocessor, we chose TI's MSP 430 F543H, and it comes with a neat little header board. This microprocessor is extremely low powered, so on its pair of its MSP 430 line, it draws about roughly 1 milliwatts of power per cycle that we operate it at, and it supports all of the necessary protocols. In our design, we chose to implement UART and I2C, so that isn't a problem for most microprocessors because those are commonly supported interfaces. Additionally, what this microprocessor also offers is that it is commercially and widely available in the form of a breakout board, and it has a myriad of pins, or extra pins I should say, that allows the user to add more peripheral devices if desired. For the sensor, like I would like to iterate again, we need it to be low powered, and additionally, we want it to have some practical application to it. And for a car environment, temperature is a good indicator of well, it's usually a good indicator of engine failure. So if something's wrong with the engine, temperature usually fluctuates a lot. So for this reason, we chose TI's TMP102 temperature sensor. This sensor is ultra low powered. It draws about 10 milliamps of, 10 microamps of current in its active mode. And it uses I2C. Now, this sensor is also available in breakout board format, and this is particularly important because normally ultra low power sensors are available as only ball grid arrays. And as some people might know, ball grid arrays are very hard to surface mount onto a device. So it's commercially available, it's efficient, and basically very low powered. So for our sensor and microprocessor implementation, we use I2C and UART. This picture on the right is the breakout board schematic for the TMP102 temperature sensor. It uses I2C to communicate with the MSP F5438, as mentioned earlier. Basically, the operation of the I2C is that it uses 4 lines for communication, 1 for power and ground, 1 for power, 1 for ground. The third line's for a clock, because I2C is a synchronous protocol. And the fourth line is for bidirectional communication, which the direction of the communication is determined by the master, which controls all the peripheral devices. UART is used to communicate between the F5438, which is, as mentioned, the microprocessor connected sensor, and the Bluetooth microprocessor, the BT5190. UART is used because it's asynchronous, and the way we design our system, it communicates or sends data to the BT5190 whenever the I2C lines are pulled. And UART also uses less power because it sends the minimum amount of bits needed to actually operate. Usually I2C requires 20 bits on a standard protocol. The first 10 is for the address, and the second 10 is for the data transfer. But because UART is asynchronous, it doesn't need the clock, and it basically sends the data whenever needed, and the receiver just pulls the input.
Okay, so now I will talk about the energy harvesting, and specifically we have picked the MicroPelty Core 7 module for a number of reasons. The main reason actually we picked this device is due to its configuration capabilities. So first, we are able to change the output voltage based on the resistors that are on the board, and to work with the other components of our device, which operate at 3.3 volts. Secondly, we are able to change the capacitor on this device. It comes fabricated at 100 microfarads, and we can change it to a bigger size to store more energy. Thirdly, the practicality of it is that we can put it in the car engine, and it will get the exhaust heat from the engine, and we don't have to worry about things such as if we use solar energy, whether it's night or day, and the user can only use this device if there's enough sun out, or a situation like that. Also, it is small in physical dimensions. It's 33 by 43 millimeters squared, so if it's within the customer's requirements in terms of size. Oh, sorry. Okay, so now we'll talk in more detail about how the MicroPelt is working with reference to its schematic. The energy harvester is harvesting this energy, this thermal energy from the engine, and then it transmits this energy into a small voltage signal. It then goes through a DC booster to make the voltage signal much larger. And so over time, this signal is stored in, the energy is stored in the capacitor, and once the capacitor is reached over the voltage over the capacitor has reached over the threshold voltage of 4.1 volts, it will then go to the output signal and transmit a nice DC signal. So once this happens, it will be able to power two main components of our device, which are the sensors and the microprocessors. So the microprocessors and the sensors are on average taking 1.5 milliwatts, and with our device we can provide about 2.1 milliwatts. For the Bluetooth device, we have decided to use a AA battery source because since this requires about 35 milliwatts, we would have to get a much larger capacitor and wait for it to store energy so that we could power it. And from my calculations, this would take on average 38 minutes to be able to get the data from our device. And if we use a battery source, we can get the data from our device every 20 seconds, which is much more practical. And yep, so.
Hi everybody, so I'm going to talk about a little bit about the Android application we developed for the system. So there are actually three chief goals that we have to fulfill for the application. The first one, as you see on the screen, is retrieve data sent from the Bluetooth module. And the second one is decode and process data into the readable temperature values. So it's like 21 Celsius degree, it's all in Celsius degrees. And the third is to display values on the GUI to the user, which is also displayed here on the photo. It's a WhatsApp icon there. And therefore, in conclusion, the Android application will decode information from the Bluetooth module and from the Texas Instrument and display it on an Android phone screen with a system level of 2.3.3. And here I'm going to show you guys a simplified flow diagram of the program. So as we can click, once we click the icon, it goes to start and it goes to a Bluetooth chat. And this is the main activity that displays the current chat session. It will check whether the Bluetooth on the Android phone is on or off, like here. It will check in the second step, and then if it is off, then it will prompt the user to turn on the device. If the Bluetooth is on, it will ask the phone to keep searching the devices within the detectable range. And then we go to a device activity list, and this activity appears as a dialog. It lists any paired devices and devices detected in the area after discovery. When a device is chosen by the user, the MAC address, which stands for Media Access Control Address of the device, is sent back to the parent activity in the result intent. So as we see from the right bottom picture here, that's how it works, the device activity list. And then after we pair a device, it will go to a Bluetooth chat service. This class does all the work for setting up and managing Bluetooth connection with other devices. It has thread that listens for incoming connections, a thread for connecting with a device, and a thread for performing data transmission when connected. When this class is finally called, it will tell the Bluetooth chat class to display the data. In our case, it's the temperature values. So on the Android phone, and the application will keep updating the temperature values about every 30 seconds, or when the supply voltage from the micro-power energy harvester reaches about 4 volts. So every 4 volts will update the value. So this is our system in general. That's the phone, and on the left side, all our systems. And this is actually a picture of when the Android application is working. So as we see from the right side, when the voltage every time reaches about 4 volts, there's a temperature update on the right side of the phone, And thank you. Any questions?
Yes.
You have to pre-pair the device with the Android phone in order to be able to set up a Bluetooth connection.
Yes, currently that's how it's set up.
So if I brought in a different phone, I couldn't use it because I have to go find the device and actually somehow.
No, you'll be able to use it. So the device would be giving off a signal that it's there. So you would have to first discover it and have to repair on your new phone, and that would work.
But usually, in order to pair, you need to actually give a pairing password.
Yes.
Which
So at the moment, it's not very secure, and the password is the default 4 zeros. So that's how it works.
Yep.
You were claiming that there's about 70 pounds of copper there, right?
Yes.
Now, as you remember, the beams, front beams and start lights and all those, and the powertrain where you turn the engine on, all of those wires you cannot change. You're talking about high beams that take 3, 4, even 10 amps, right? So that you cannot change those wires. What we are talking about here is maybe connections of small signal wires, but those are now fiber optics anyway, so I don't see the point that you are claiming here. You shouldn't do that. Because how could you change a wire from, let's say, from a battery to those different systems that goes into starter motor? Starter motor requires about 300 amps to start. Every light bulb when you put your hand on or when you, let's say, push the brake, the back lights are each 2 amps. You've got to deliver a very high side wire to do it. So what is this? Well, you need to be careful when you're claiming that you will remove the wire.
So I think the misconceptions that were. Okay, so I think the misconceptions that you're thinking that we're removing all the wiring in the car, which is to an extent not true, because as you mentioned, power lines can't, we can't support like 300 amps of power. But what we can do is remove all the wires. The way we design our system, 70 pounds of wire is one of the benefits, but another of the benefits that we're interested in is the hazards that the actual wires cause. So, if you have a loose connection somewhere, it could potentially, in this worst case, like start a fire in the engine, which can be really bad for the car.
I just wanted to say something to what Kevin said, and also we're reducing the wires we're making our device easily portable so that it's not connected directly to the car. So we're making this new device for this car engine, and if we want to move it to another one, we won't have to worry about wires or things of that nature. So in essence, we're reducing it by designing new things that won't connect to the car and add on to the wires.
One more question, because we're running out of time. Ron?
Did I hear you correctly? You said that the energy harvesting device can provide something like 2 milliwatts of power.
Yes.
Whereas the Bluetooth requires something like 30 milliwatts, so you use the battery for Bluetooth?
Yes.
Which means of your total power needs, you're only really energy harvesting about 10% of it or whatever. Is that true?
Yes, so we could have provided a higher power, but it would take a longer time to charge up the capacity. So we could have put a bigger capacitor to store higher energy, but it would have taken longer to transmit data.
So I have a follow-up question then. Since the energy harvesting device apparently doesn't harvest a lot of energy, have you looked into what would happen if you have your car in Alaska where it's cold? The engine may take much longer to heat up, or maybe it doesn't get that hot. How would it work in that kind of situation?
We didn't investigate those types of situations. We designed it for just a basic car engine, which is about 90 to 110 degrees Celsius. So we just use the average temperature of a car.
Also in response to that, it would still work. It would just, so the way it works is that it would take a much longer time for we to actually deliver. The delivery would be more delayed. Instead of, at the moment, it's operating every 20 seconds if the car's engine is at 100 Celsius. However, if the car's engine was at a lower temperature, it would, we haven't thoroughly tested as to how long it would actually take, but the capacitors would still charge. It would just take a much longer time.
All right, thank you.